Well, good evening, everybody. And I'm back tonight to talk about part two of what we started a couple of weeks ago. We're going to talk about the more modern stuff now. We talked about what that was an introduction and what I called the golden years of radio, but we're going to talk about from World War II and the post-war era up to present day. And so this is what we'll cover this time. So what we're hello, where are you? There we go. What we're not going to talk about is, like I said before, we're not going to debate about who's got the best receiver. We all know who's got the best receiver. Everybody there knows the best receiver. It may not be the same receiver that's the best receiver, but we all know what the best receiver is. That's our opinion. So that's no problem. I'm not going to give any recommendations on those either. And I'm not going to bash any particular receiver or radio, like I said last time, unless it really deserves to be bashed. And there's a few of those out there. And I'll just quickly show a picture of one of those right there. We'll talk about that later. My disclaimer is always, these are my opinions expressed. They're strictly my own. You can disagree, and that's perfectly fine. And I'm willing to discuss anything, but these are my opinions. No problem, and I'm sticking to it. So, what are we going to talk about tonight? We're going to talk about the changes that came about from World War II, where how technology changed. A lot of things came out of World War II that we kind of take for granted today. We're going to go add some more defining moments in receiver development. One thing I'm going to do is go back and look at James Lamb's ideas, and do they still hold true today? The stuff that he published back in the 30s, which is pretty interesting. And of course, the question I get asked a lot by many, many people when I used to do the maker fairs all the time, would somebody please explain software-defined radio? And then I'm going to talk about what may come next in receivers. So again, a little bit about me. I'll do a little bit of my background. Yes, I am you see my pictures on QRZ. I'm an obsessed radio collector. But I like to collect radios that to me are technologically important, things that had an impact on development and development of receivers and radio technology. And I started in the 1960s collecting this stuff. Still got radios that I had back then. I still do it. I'm still at it. And of course, I learned a few things. Like I said before, I'm fascinated with this history of radio. It's pretty amazing. One of the interesting things that I didn't mention last time, over 30 years as an engineer, actually closer to 40. The time I did this, that's right. At the time I originally wrote this, it was 30 years. That was a long time ago. It's closer to 45 years as an engineer when I hit retirement. But I finally got to work with radios in my job, and I got paid a bunch of money to do it too. So that was pretty cool. Uh, Speaking of military and that type of stuff, yeah, we were doing battlefield radio systems. So that was a lot of fun. So as a review, what makes a good receiver? It depends on your application. We talked about cell phones, communications, in our case, radio communications, radio astronomy, et cetera, et cetera. We want to talk about communications receiver and what makes a good communications receiver. And of course, that's being able to detect signals down to the noise floor. Basically, what's called minimum discernible signal, or MDS. Be able to withstand nearby strong signals, because we got a lot of those on the ham bands. We want a wide dynamic range, and of course, those two things are kind of counterproductive to each other. Having a, a wide dynamic range and being able to withstand wide dynamic range, getting down to the noise floor, and being able to withstand nearby strong signals, those things are kind of counterproductive to each other. So it takes a good balance. You want to be able to hear the signal that you're interested in. You don't want to hear all the other interference, adjacent stations, and what have you. And you want a receiver that is stable and resettable, or you tune back to the same frequency every time. And I'm happy to say that that was defined by James Lamb in 1932. He was the technical editor for QST back then. And the question we're going to talk about is, do those still hold true? And I will say right now, decidedly so, they do still hold true today. So he defined a lot more than that, but those are the things we're interested in right now. So I talked about defining moments, and I'm going to review what we did last time. And the first one up was Hertz proving Maxwell was correct that electromagnetic waves. We know about that. And of course, Fleming developed his oscillation valve, which we know as a rectifier, a vacuum tube rectifier. Good old DeForest invented the Audion, or the triode vacuum tube. It wasn't a very good tube, but it worked. Fessenden came up with the heterodyne principle, which we're very aware of today. It's very common. We use it in everything we do virtually with radio. Armstrong, genius, regenerative detector when he was in college. Amazing guy. But he also came up with the super heterodyne receiver based on the heterodyne principle. Browning and Drake, a couple of more really bright guys, came up with a better regenerative receiver that wasn't encumbered with the patent wars. And of course, I mentioned James Lamb publishing in QST. So that was number 8. So what's number 9? What have we got? Well, I think one of the really important things that happened was this fellow, Schottky. And many of you know that name, and it is the same Schottky. You know about Schottky diodes and all that stuff. He was working at Siemens back at the early, the 19 in the teens, okay? And he developed the tetrode and the pentrode. Pen, easy for me to say. Pentode while he was working there. And of course, the tetrode and the pentode were radical improvements over the triode. They really helped improve the performance of the vacuum tube, kind of eliminating some of the issues that encumbered the triode. We talk about it, interelectrode capacitance, and I talked last time about the Neutrodyne, how that was used to eliminate the interelectrode capacitance in a triode. Well, the tetrode and the pentrode developed that further. Well, the problem was they weren't widely available, and they were very costly in the early days. So they weren't widely used. And it wasn't until really the 1930s that they started to catch on. And what was going on in the 30s? Well, there was a big burst of development technology in the late 30s because of World War II. World War II, of course, contributed to defining and refining that tube technology, obviously. It provided great improvement over the triode. We've got all the problems that we had with triode-based receivers suddenly become less of an issue when we're using tetrodes and pentodes. We get high-performance super heterodynes. They're starting to come out, and I talked about those last time, the AGS and the Comet from National and Hallicrafters, respectively. Those popped up. But the problem is they're still expensive, but not for a government at war. So that's where the technology really blossomed. So during World War II, what happens? Receiver technology was evolving during World War II. We're getting better components, we're getting better performance, better materials, higher density construction because things are being reduced in size. We're making things smaller. A good example of this, if you're familiar with a BC 392, or I'm sorry, a 342 versus a BC 348. The BC 348, they're basically comparable receivers from World War II, but that 348 is probably half the weight of the 342. 348 is half the weight of the 342. I'll get it right. But they're comparable in all, they're both airborne receivers, but that 342 just weighed a ton. They're massive. Steel. Aluminum made the difference there. But new applications came out of World War II. What about going VHF and UHF? We suddenly have a lot of UHF communications where it's more like what we considered UHF. In the 30s, UHF was considered 28 megs. 10 meters was considered UHF. 6 meters was super high frequency, and actually 5.5 meters in those days. Super high frequencies, what we consider microwaves today. So VHF, UHF, new applications, a lot of new products coming out, and a lot of new vacuum tubes that handle VHF and UHF applications. And of course, the big one, radar. Radar was a huge contributor to technology during World War II. So some examples of some of the things that came out of World War II, and this is what really bolstered amateur radio in the late 40s and early 50s, was the availability of war surplus. I would dare say that many of you guys here tonight have seen a lot of what I'm going to show you in the next few minutes here. like the BC-348. How many people here started out with a BC-348 as your first ham receiver? They were there were thousands of them available after World War II and in the early 50s in surplus, and they were very inexpensive. But take that a step further, even more and even cheaper were these guys, Arc 5s. That was my first amateur receiver, was an Arc 5. It happened to be a 696, or yeah, BC 454, sorry. It was a BC 454 receiver, which was the 80-meter band. That one right there is kind of a rare one. That's broadcast band. So that's kind of a cool little receiver. And that's out of all this is out of my collection here. Um, Speaking of UHF and VHF, a lot of hams got these guys and put them on 70 centimeters. This is a radar set that runs on 70 centimeters. Tail end Charlie. It was used in P-51s as a detector when somebody was coming up on your stern, and it had a receiver and a transmitter. And that you can see that it's got this phasing line there, so that the receiver and transmitter can share that same antenna. We have used some of that kind of technology again today for things we do. The other one that came out at the end of World War II is the ARR-15, and I'm going to talk a little bit more about that later from Collins. This one was kind of an interesting one because it had something called auto tune, and it used preset channels, so nobody had to fiddle with the controls. You just flipped the switch and it changed to a different channel. So this was kind of an important piece of equipment out of World War II, but a lot of hams ended up with these. That one's kind of a beater, but that one is also out of my collection. But while I'm talking about the ARR-15, what I think was the next defining moment was the development of the PTO by Collins. PTO, otherwise known as a permeability tuned oscillator. This was developed during World War II by Collins, and the whole idea was to use a variable inductor to change frequency instead of a variable capacitor. So using a variable inductor meant that it was more stable and it was resettable and it was linear, which is really a really important thing. This was first introduced during World War II in what was called the ARC-2 transmitter receiver. It was a combined transmitter receiver. But in 1947, Collins introduced the 75A1 amateur receiver, which used a PTO. And that was their very first amateur radio receiver. And it was using PTO for stability and really kind of an impressive radio, double conversion. We talked about that, super heterodyne double conversion. So it's got two IFs. And of course, this introduced the A line, which culminated with the 75A4 in the late 50s, or really actually mid 50s, I guess. And they embraced single sideband. And we'll talk a little bit about single sideband, embraced with the single sideband with the KWS1, otherwise known as the Gold Dust Twins. Why were they called the Gold Dust Twins? Because it took a lot of gold to purchase the darn things. $5,000 in around 1955. So that was a bundle of money back then. But what it led to is a lot of other manufacturers getting on the SSB bandwagon, single sideband bandwagon, and for good reason. SSB was a big improvement over previous AM. Well, a little bit about Collins A-line receivers, and these are some from my collection at 75A1. That was the first one they introduced. I happen to have a really low serial number, two of them, and another one I have is a really high serial number. We think it may be one of the last ones that was ever made. So that was kind of cool. 75A, that's a 75A3 and the 75A4. So these are all the A-line receivers that were manufactured in the late 40s into the 50s, 1947 and 1958. So quite a good production line. Of course, these were replaced by the Collins S line. So let's talk a little bit more about single sideband. It was just starting to appear in amateur radio. Manufacturers were getting involved. The roots of it go back to the 30s, but it's starting to appear in amateur radio more mainstream in the late 40s, early 50s. And it was a huge battle. You think about today. Today, we've got the battle over FT8. Back then, it was the battle over single sideband. So things don't change. A lot of manufacturers were getting involved. Of course, I mentioned Collins, certainly. Central Electronics was a big one. They were building transmitters, but they also built what I call a receiving converter. They referred to it as a slicer that allowed you to take a regular AM receiver, your standard super heterodyne, add this box out board, and it would allow you to select upper and lower sideband. So that was a useful device. You didn't have to have a new receiver. You could use your old receiver. Of course, Collins, I mentioned. Drake was another one, the early adopter of sideband, and they came out with something called a 1A receiver, which is a rather odd looking radio. It's sideband only receiver with an odd form factor. And for the life of me, friends of mine and I have debated about why it had such an odd form factor, and probably because you're adding this to an existing station, possibly single sideband. You've already got your big AM receiver, your Hallicrafters, your Hammerland, or your Collins A line, or whatever that takes up a lot of desk space. This doesn't take up very much desk space, but it was a good performing receiver, and that's one out of my collection as well. A neat little radio, very different looking. So a little bit more about sideband history. You may be surprised to know that single sideband goes back to 1915. The patent was applied for in 1915. A fellow by the name of Carson, he recognized that AM consisted of a carrier and two sidebands, an upper and lower sideband. In 1923, he was finally granted the patent. Okay, so who is he working for? Bell Labs. Who's adopting single sideband? The phone companies, Bell System. So they were the first ones to use single sideband, and they were using it on their transatlantic circuits in 1927. So on a single radio channel, they could have two voice channels. So that doubled their capacity instantly when they switched over to single sideband. So they doubled their capacity on their circuits without adding, basically not adding any very little new equipment. If you think about it, it didn't take a lot. Eventually, it got into the wired circuits in the 1930s. Again, this is doing two voice channels on a single carrier, which is cool. We call that, in a sense, frequency division multiplying, right, or multiplexing rather, FDM. So amateurs were experimenting with it in the 1930s, but it really didn't gather acceptance until the 1950s. And of course, one of the big things that came about to bring single sideband out in the 50s was a project with Strategic Air Command, Curtis LeMay, and Art Collins, something called Project Big Talk, where they stuck KWS-1s and 75A4s in airplanes and flew them all over the world to prove that single sideband was more efficient at global communications than AM. So there you go. And today, on international flights, we use single sideband communications, whereas locally on HF, whereas local regional communications is VHF on AM. So this made an impact. A little bit more history. I want to talk about three methods of generating single sideband. Of course, this is just a little bit about the technology. We talk about the filter method, where this is the most common thing used. We remove the unwanted sideband with a bandpass filter. So we allow the one we want to pass through. Okay, so that's how we get rid of the unwanted sideband. Another method is called the Hartley modulation, but most people know that as phasing method. And this was pretty common back in the early days of single sideband. Guys like Central Electronics, Hallicrafters, and others used this phasing method, but it was fraught with problems. But it uses a 290-degree phase shift networks, one for audio and one for RF. And of course, those are touchy, and they're difficult to keep them stable and all of that. So there's problems with the phasing method. Adding or subtracting the results in lower sideband or upper sideband with this 90-degree phase shift. That's going to play a role again. We'll talk about that shortly. The third method was called Weaver modulation, that was developed in 1956. It was kind of an extension of the phasing modulation, but instead of doing the 90-degree phase shift in audio and RF, it just did the 90-degree phase shifts along with what's called a quadrature mixer. And again, I'm going to talk more about that later. This is just informational at this point. It's centered on a zero frequency, and then it's translated up or heterodyned up to the frequency you want to operate at. Zero frequency. That sounds like direct conversion. Sound familiar? Anybody who's into QRP and direct conversion knows all about that stuff. So Weaver modulation plays a role. This becomes an interesting thing later on. So 1950, I don't call this a defining moment. I think it was just an evolutionary thing with Collins developing the mechanical filters. At the time, the existing technology was crystal or LC filters, inductors and capacitors and all that. So they tended to be, to make them really high Q, to make them really narrow and good band. They had all kinds of problems. They weren't really, really nice, clean filters. So Collins had been developing these filters for the phone industry. Remember single sideband? Yeah, they're the ones that were supplying filters for the the filter method of generating single sideband for the phone circuits. Collins was big into that. They tended to be around 50 kilohertz, by the way. That was their center frequency, their IF. Those are used in those multiplex circuits. They had very steep skirts and low loss compared to crystal or LC filters. They were a big improvement. Well, Collins decided to apply that to communications receivers, and it started with what was called the 75A2A. They added crystal filter or mechanical filter to that radio. And boy, what an improvement. And that just caught on. Everybody started using mechanical filters. Again, I could consider that a defining moment, but it's like, yeah, that was some technology that was around. It was just reapplied and kind of an evolutionary thing, but a big deal. Today, where would we be without them? Of course, these are the receivers that used them. The R390A was a cost reduction of the R390, and R390, and this is again my opinion, and it's shared by many people, is arguably one of the best receivers that was ever made, and it was developed back in the early 50s. It's a pretty incredible piece of hardware, and it evolved from that 51J series receivers. Believe it or not, the first R390 contract was in 1952. The last R390A was manufactured in 1984. So that had a long run. Amazing. 1984. There's a story about that, but I won't waste. We can save that for another day because it's an interesting story, but I won't go into that right now. Why would they build an R390A in 1984? Okay, so some of these receivers, 51J3, otherwise this one is known as a URR23, which happens to mean that it's got its own cabinet. Most of these things were rack mounted. This one happens to have its own cabinet, desktop cabinet with matching serial numbers. So it's a pretty special radio. They're very rare that way. Of course, the ubiquitous R390A. Don't ask me how many of those I have. I got a bunch of them in all different shapes and forms. That one happens to be from EAC, Electronic Assistance Corporation, which was a joint venture between Hammarlund and the US government. Collins didn't have the capacity to manufacture these things fast enough for the government, so they contracted out to many, many other vendors, including Maybelline. Yeah, the cosmetic manufacturers. So, and then of course the SP600. The SP600 was a evolution of the old Comet. I mentioned the Comet that was kind of a prototype. The Comet Pro that became the Super Pro 100, 200, 400, and 600. This is the Super Pro 600. This one right here happens to be a variant of the SP600 that is called was manufactured by a company called Dero Research, called a 2F, and it's a VLF receiver. Now Hammarlund made a VLF version called an SP600L. This happens to be one that was manufactured by another company. So it's kind of an interesting receiver. So let's talk about something else going on here. All this is taking place. I'm not considering this a defining moment, but it's important to the evolution of what's going on with receivers nonetheless. This started in World War. Actually, it started before World War II, but primarily World War II. Manufacturers were integrating receiver and transmitter into a single unit. A lot of cost savings there. It really began in the 30s and 40s, believe it or not, in amateur circles. But it was really World War II that really drove this. By World War II, the transmitting and receiving schemes are very similar. You basically take a receiver and you turn it around and you got a transmitter, right? You think about it. So you can share a lot of circuitry. So there's a lot of economies to be had, fewer components, a lot of shared parts. So that makes a big difference in functionalities, shared functionality, like your IF is shared on a transmitter and receiver if you use a similar scheme. A lot of manufacturers, or I should say several manufacturers, opted in back in the 30s, and this is where this stuff started. You'll see something like 1930s, the national radio had something called a TRW. This was a super high frequency transmitter receiver. So it operated on 10 meters and 5.5 meters. And it was called a TRW, transmitter receiver in a wooden box. That's how it got its name. I happen to have three of these. Two of them have been restored, and I was looking for. I don't have any pictures of them. I wanted to throw the pictures in here because they're really a neat little radio. They're portable. You can carry it around on your shoulder, battery operated, really neat. Also in the 1930s, RCA introduced something called an ATR 219. This was another 5 meter, 5.5 meter transmitter receiver in a single box. That thing sold for $29.95. Amazing. That was a lot of money back then, right? Along comes the war. Now, the war shut down amateur radio here in the States. And the government introduced something called WERS. If you've never heard of that, that's the War Emergency Radio Service. And a lot of amateurs volunteered for that. They were allowed to operate on VHF and UHF. So ostensibly 2 meters, 1.5 meters, or 1 3/4 meters and 70 centimeters. So 144, 220, and 440. Abbott manufactured this thing called a TR4, which they called a 2 meter handy talkie. I call it a luggy talkie because it was a rather large radio. It was battery operated, but it was introduced in the WERS version on a different frequency. After the war, they introduced it into the ham community on 2 meters when we actually got 2 meters. So that was an interesting little thing. And it's basically a transmitter and a receiver in a single box. Helicrafters, I don't know if you've ever run across one of these before. It's kind of an unusual one, an SR-75. That was actually an amateur receiver that had a 10-watt crystal controlled transmitter built in. Kind of a neat idea. Maybe one of the first amateur transceivers, eh? And of course, everybody thinks about this one as being the first. It really wasn't. There were these other things came along first, but Collins KWM1 was the first sideband transceiver. It's very, very compact, very lightweight. It found use in a lot of airborne applications, most notably on the U-2. There's a lot of stories about that. But KWM1. But there were a host of others that got involved in building these things. Helicrafters, Cosmophone, which is something you may not have ever heard of. Night kits, Allied Radio, night kits, Gonset, which many of you have heard of, and so on. There's lots of them out there. I don't want to forget Heathkit, but that came much later. Some examples. There's the TR4 from Abbott. Kind of a funky looking little thing. It's a separate transmitter and receiver, and it really didn't share a lot of things other than the cabinet. Of course, the Gonset, the original Gonsets, communicators, a communicator 2, which is what that is, and a communicator 3, communicator 4, all these things were transceivers for 6 meters and 2 meters, and quite popular back in the 50s and 60s. Quite a nice little unit. That one, crystal controlled transmit and a tunable receiver. There's the KWM1 with its matching speaker. That's out of my collection here. And of course, that was an interesting radio. It only operates on 20, 15, and 10 meters. It doesn't do 80 and 40. There wasn't room for the coils inside that little box. And one you may not be familiar with, which is a pretty amazing radio, is the Helicrafters FPM 200. This came out later. It was all solid state, and they did not make many of them. They're quite rare, and they go for gobs of money. Thousands of money, thousands of dollars for these things when they turn up. Kind of a neat piece of gear, though. But this all leads to, I mentioned Helicrafters FPM 200 was solid state. So what's the next defining moment? The BJT, the bipolar junction transistor, of course. Well, the transistor development goes back to the mid to late 40s with the team of Bardeen, Brattain, and Shockley at Bell Labs. They were building, this is their point contact germanium transistor. So you can see this is, I think this picture came from the Smithsonian. I think it's a reproduction of it. I don't think it's the original piece, but it's a point contact transistor with a germanium crystal. So one of the problems with this thing is even the production versions were extremely fragile. Don't drop it. So they had a lot of issues, but some important things about the germanium transistors is the base to emitter voltage is much lower than on a silicon transistor. It's typically like 0.2, 0.25 volts compared to 0.6 volts on a germanium silicon transistor. So a little bit of difference, a little bit different biasing and what have you. But some things that make them desirable in certain applications. But it was Shockley that came up with this idea of the bipolar junction transistor in 1950. And it was a lot more rugged. It was a lot more predictable how the thing was going to behave. You could drop it and it wouldn't break. That was an important improvement. Uh, One of the first ones out there was a good old CK722, introduced by Raytheon in 1953 to the hobbyist market. It turns out that Raytheon was manufacturing two other transistors, one of which was a CK721 that was being used in, I think, in the telephone industry, primarily as an audio amplifier. And their rejects, which didn't quite meet the 721 specs, but were fine for hobby applications, became the CK722. So a 721 would sell for $30. These things sold for like $395. Still a lot of money back then, but so Raytheon held a design contest. They had $10,000 awards in prizes for their design contest. And here's a little ad. There's the advertisement. I think that was out of Popular Mechanics, $10,000 in prizes. And there's a CK722, an original one out of my collection that ostensibly came from Bernstein Appleby, if anybody remembers that company. Good old BA, Bernstein Appleby. But that's a CK722. I've got quite a few of them, but that's one that's got the original packaging, which is cool. And of course, Raytheon, their contest, these are the projects that came out of that. And I think that's interesting. Number one was a CW filter. So that's kind of neat. So the question that always comes up is, those of you who were around back then, what did you build? I remember my first project with a CK722. That was back around 1964. I built a code practice oscillator. What else? You build a single transistor code practice oscillator right out of the book from ARRL. So you want to become a radio amateur. There you go. So it was successful. Okay, so what came out of this? The first successful transistor radio. It wasn't from Sony, as everybody likes to think. Sony popularized it, but the Regency TR1 was introduced in 1954 at a price of $49.95. It contained 4 Texas Instrument NPN devices, and they made about 150,000 of them. But not to leave Sony out, Sony is the one that brought the transistor radio to mass production and introduced it, really made it commonplace. So that was a big step, going from vacuum tubes to transistors in a basically a broadcast radio, AM broadcast band radio. It was a big step, really cool. But before YACOM would, let that sink in for a minute. There were several US transistor sets. A couple of companies made them. Notably, Davco, DR30 in the mid-60s, kind of a neat little radio. It was a very early solid state ham receiver. It even used a field effect transistor as its first RF stage, a FET. These are rare, only about 600 were made. I had 2 of them, which I no longer own, but they were a neat little radio. Really enjoyed having that. It's very elegant. I call it an elegant and compact design, my opinion, but it really was small. It's half the size of a typical receiver today. So very, very compact. National introduced the HRO 500, which was another transistor set. And there's one sitting right over my shoulder, right over there on the table behind me, as the HRO 500. This was a very, very good receiver, but it did suffer from issues. I have to admit that it had problems, but it was an extremely accurate frequency display. That's something that was tough up to that time, but it's very accurate display. It used an up-converted first IF. Up to now, everything's been down converted, like down to 455 kilohertz. The problem with down conversion is you generate images, and so you get a lot of spurious signals in your passband. Up converting moves the IF out of your receiver's tuning range and reduces the spurs and images. So it's a really good scheme. The problem with it was that they used germanium transistors. Some more on that in a minute, but the other key thing to this was this high stability phase lock loop heterodyne oscillator. So that's the oscillator that determines which band you're tuning. So that's that heterodyne oscillator, not the VFO. The other one that came out around this time was the HQ215 from Hammerlin. There's one of those sitting over on the shelf here. In fact, it's the one that's illustrated in here. That wasn't that great a receiver. It looks nice, but looking nice and working well are two different things. It did have performance issues, but the biggest thing with these two radios were the germanium transistors. That was a problem. Um, the designs were not much more than substitution of transistors for tubes, and that really didn't do a good job. So here's the Davco. It's a cute little thing. You get an idea. That's about what, maybe about 8 inches wide and about 4 inches high. And it had a matching power supply and speaker that went with it. It's ham bands only and WWV. I want to throw that in there. There's the HRO 500. And second to the last receiver that National made, the HRO 600 was the last one they manufactured, was all digital, a lot of digital electronics in it. Quite a change from this one, but this is all germanium transistors, and of course the Hammerlin HQ215. What was interesting is they duplicated the conversion scheme of the Collins S line. So you could essentially take this receiver and plug it up to your 32S1 or your 32S3 transmitter and transceive with them. They work together. That's kind of an unusual thing that they did. Well, things did improve after this. The things were improving. Of course, we know Kenwood, Yaesu, and ICOM, they evolved some really great receivers. They still are evolving great receivers. It grew out of a use of some specialized LSI components, large scale integration. We'll talk about that term in a little bit. Of course, high volume means low cost. That's what the Japanese were really good at. And of course, you guys know these radios, the TS520, the 820, the 950, and the TS590S. These were great radios in their day. ICOM, the 781 was a great radio back in the day. How about that culminates with more recently with things like the 7800 and the ICR 9500, which is just strictly receiver. That's a beautiful receiver that runs you around $12,000 if you're not familiar with it. Not an inexpensive radio. Of course, Yaesu, they came out with the FT101, which is a wonderful radio. I've had quite a few of those over the years, still have 3 or 4 of them here. But they went on to develop the FT1000D, which led to the Mark V, and ultimately, more recently, I'll talk about the more recent things later, but recent decade, the FTDX 5000, which was another superb radio. And of course, I don't want to forget our US manufacturers of Ten-Tec and Elecraft. Elecraft has come out with some just fabulous equipment in recent years. So no question about that. Well, some of the early solid state attempts, I talked about the HRO 500 and the HQ215 being problematic. They weren't really high performance equipment. The idea was replace the tubes with transistors. This sounds like a great idea, right? Oh man, we just take the existing design. I go from this big tube to a little transistor. It's going to get so hot. It's going to be smaller. It's going to draw less power, so it's not going to generate as much heat. This is a great idea. Well, it didn't really work very well. The big problem with changing over to transistors was a limit to the dynamic range of the receiver. Tubes are really good with high dynamic range. Transistors, not so much in those days. So some attempts were made with hybrids using tubes and transistors. It still had lower power consumption, but they really didn't have good, strong signal performance. That was the problem. And it's that dynamic range thing. Everybody forgot about Lamb and his principles back in QST in 1932. So it took a few years, but they figured it out, thankfully. Well, defining moment number 12 is an interesting one. And this is a kind of the key to everything where we are today, the digital communications age. This officially started in 1948, believe it or not. A fellow by the name of Claude Shannon at Bell Laboratories published an article in the Bell Labs Tech Journal called A Mathematical Theory of Communication. Essentially, he's saying we can take an analog signal and convert it into a digital signal, process it, and then turn it back into an analog signal. And this is big deal for the phone companies, right? Analog, digital, analog. You use an A to D converter, you transmit this stuff over long distances digitally. You have lower losses incurred, and then you convert it back to analog. So you have digital phone lines. Great stuff. This is what this was coming out of. This is the founding work for what we now call information theory. And it's based on a couple of guys, Nyquist and Hartley. If you've ever heard of the Nyquist sampling theorem, Nyquist is an important piece of this. It's the basis of all of what we do with digital software-defined radios and all of this. Nyquist says that you can take any signal, sample it at half the fundamental frequency of that signal, and reproduce that signal at a later time from those samples. So it's an important piece. This, of course, like I mentioned, leads to digital communication systems. Principally, the phone systems went digital. Telephone systems, of course, computers obviously are all digital, and they're using this same mathematical theory, information theory, and of course, eventually radio it evolved into. Unfortunately, it's just an accident of history. In the very same issue of the Bell Labs Tech Journal, what was published? Schottky's article on the bipolar junction trend. No, actually, no, it wasn't. It was the other guys. It was the junction transistor, not the bipolar junction. But the Bell Labs Tech Journal published their first article on the transistor. And of course, nobody paid attention to Shannon's article about information theory and go, what's that? The transistor. Now, there's something really special. So it took a few years for that to catch on, needless to say. And interestingly, one of the first users of that technology, information theory, digital signal processing, was by Collins in 1984. They introduced something called an HF2050 receiver. This is a low frequency, medium frequency, high frequency. It covers 5 kilohertz to 30 megahertz. It was developed for the Canadian Air Force. It was very expensive, about a $35,000 radio. The final IF and filtering and demodulation are done in DSP. So it has I believe it's a 90, I want to say 90 megahertz first. So it up converts 90 megahertz first IF, and then it goes into the DSP where it does that second IF, doing all the filtering and demodulation. That receiver today, they go for several $1,000s. They're still in demand. It's a great receiver today, Dennis's opinion. Without a doubt, of all the receivers I've ever used, that has the best noise reduction of any receiver I've ever encountered, including some of the latest stuff out there, like the Flex radios. It's just a marvelous receiver. But interesting stuff. They only made about 1,000 of them, so they're kind of hard to come by. But in the amateur market, I won't call market, let's say the amateur experimentation field, the first application, the DSP, popped up in QST in 1999. Some of you probably remember this article. It's this little guy right here, the DSP-10 from W7PUA. It was published in a series of articles in 1999, and it uses a Texas Instrument digital signal processing chip. This is a 2-meter transceiver. Okay, it has a computer graphical user interface over a serial interface. Yeah, we didn't have any USB stuff back then like we've got today. So it had a computer GUI with a spectrum display. Wow, talk about ahead of its time. No knobs. You tuned it with the keyboard. And of course, this defined what was to come from there. So interesting stuff. Curious question for anybody: if you've ever built, if you're familiar with this, if you've ever built one, I do have one in storage. It's a neat little radio. Puts out about 2 watts on 2 meters. But kind of a cool little thing. Well, oh, Dave, you're right. I just pulled up chat. I'm sorry. Yeah, I got that backwards. You're right. Yeah, it's 2 times the highest frequency. You got to sample at twice the highest frequency, not half. You sample at twice the highest frequency, and you can recover the original signal. A slip. Correct. Okay, So I'm going to turn back the clock a little bit and talk about defining moment number 13, because this is an important one, of course. Come on, where are we? There we are. And of course, we all know that the integrated circuit. Where would we be without integrated circuits today? Jack Kilby was at Texas Instrument, and in 1958, he came up with the first, what we consider the first working IC. He had multiple components on a single semiconductor body. So he had multiple components mounted in a single body. So instead of a single transistor, he had multiple transistors. This becomes known as small scale integration, SSI. So your things like your old Motorola RTL and TTL circuits, they're just single logic components, small scale integration. Okay. The origins of this actually go back before Kilby. Siemens was working on a system where they had multiple devices in a single package, and I kind of think it's like a hybrid type thing. That's in the late 40s, but not like we know hybrids today with a ceramic substrate and all of that, but kind of that idea. And TI had something they called micromodules, which were a similar thing where they had components on ceramic wafers that they could integrate into basically into a grid, on a compact grid, and make small things. But Kilby took that micromodules to the next step with the first working IC. So in year 2000, Kilby received the Nobel Prize in Physics for that little device, the integrated circuit. So let's talk a little bit more about that. There were problems. What Kilby had done was he'd used germanium as his substrate. He had a lot of problems using germanium. It wasn't very reliable. It was very difficult to isolate the components on a germanium substrate. Very difficult to isolate them. It was Robert Noyce at Fairchild that came up with the idea of using silicon instead of germanium, and that solved that problem because he could basically create a PN junction as an isolator with using silicon. So that was the big step forward. And of course, from there, we lead to the evolution of small scale integration to medium scale to large scale to very large scale to ultra large scale, where we go from 2 components on a single chip to billions of components on a single wafer or a single die. And so we go from that ugly thing to stuff like this today. So this was a huge leap forward. And of course, this leads to the proliferation of digital logic, lots of digital applications. Frequency synthesizers, there's a new one, allows to digitally generate a stable frequency and be able to have memories where we can go back and recall a frequency. We can do that with digital stuff. We can have direct digital frequency input, from a keyboard. I think this is what I believe, and I'm not sure if this is true or not. I have one of these things. I didn't take a picture of it because the display is bad on it. But I believe that is the first amateur radio that allowed direct frequency input from a keyboard, was the TR-2400. And I want to say that came out, I guess, in the late 70s. I think around 79, I think is when I think that's when I got mine, was in 1979. I bought one. A little 2-meter handy talkie with direct frequency input. Kind of cool. Well, it also leads in digital applications to digital signal processing. And of course, like everything, it evolves over time. Higher clock rates, higher performance. Higher clock rates means we can do more work and we can put more functions into that IF, right? Because we're using DSP for IF. If we start clocking at higher rates, getting wider dynamic range, more bits, bit width is what determines your dynamic range. So we get more functions. We're doing audio filtering using DSP, but now we can do IF filtering using DSP. We can generate digital filters, which can be extremely high performance with high performance DSPs. Well, turning back the clock again, another thing that popped up is, and I call this defining moment number 14, is the notion of spread spectrum. Now, this really doesn't show up in amateur radio until more recently people are experimenting with it, but this goes way back. Look at this. 1942 is when spread spectrum. Everybody hears this term, but they may not really understand what spread spectrum is. It means a lot of different things, actually. We can talk about different methods, and I will talk about those. But 1942, it's patented. And who got the patent? These guys, George Antheil and Hetty Markey. Now, who's Hetty Markey? You guys know Hetty Markey. She was an actress, right? Hetty Lamar. No, not Hedley Lamar, Hetty Lamar. Apologies to Mel. Anyway, Hetty Lamar and George Antheil hold the patent that was awarded in 1942 for spread spectrum. And he was a music composer, and he used piano rolls to control musical instruments. Well, they thought about, well, why can't you use piano rolls to control the frequency you operate on? And their application for that was for the Navy to use it to create an anti-jam radio link for their torpedoes, because the torpedoes were basically on one frequency, easy to jam, interference, all that would mess with them. So by changing the frequency quickly, it made it harder to jam, right? Makes sense. So you have an identical piano roll at the transmitter and the receiver, and they clock at the same rate, and so you switch frequencies, and you're hopping all over the place. Spread spectrum. Your signal is spread across the frequency domain. That's what spread spectrum means. And in this case, this is a frequency hopping system. That's what we call it, frequency hopping. And the Navy wasn't interested in it until 1962, 20 years later, they adopted it. Oh, well, it was jam resistant, which is the important thing. But it's important to note that that little technology right there, that little thing, it's everywhere. Cell phones, Wi-Fi, everything you touch today virtually uses spread spectrum. So there you go. You can thank Hetty Lamar and Hetty and George. There you go. So continuing with spread spectrum, let's talk a little bit about the methods. I mentioned frequency hopping spread spectrum. That's the most basic one. But we do other things like direct sequence spread spectrum. We do things like combining your intelligence signal, let's say like it's a digital data stream, with pseudo-random noise. Pseudo-random noise is not truly random. It's a repeating pattern. That's why we call it pseudo-random. So it's predictable. So pseudo-random noise plus your intelligence, you have a spread spectrum signal. And what does it sound like on a radio? It sounds like noise. So this is one of the systems. We talk about chirp spread spectrum. We talk about time hopping spread spectrum. There's lots and lots of different techniques of doing spread spectrum. Frequency hopping is probably the one most common people think about is the frequency hopping method. But anyway, there are advantages, of course, obviously, privacy. And boy, if you use encryption systems on top of that, it's really private. But privacy and especially the immunity from interference, and this is a big one, both natural and man-made noise, jam resistant. So it's an anti-jam capability, right? The other thing that's important for certain applications is reduced probability of detection. Like if you're trying to be stealthy with your radios, spread spectrum makes you quite stealthy. So that's an important thing. It looks like noise, right? So I don't know whether to call this SDR the defining moment of, or SDR origins defining moment 15, maybe not, but it plays an important role in software-defined radio. And it's this thing called FFT. You've heard this term, I think, probably many, many times. It's developed in 1965 by these guys, Cooley and Tukey, the fast Fourier transform. And in 1965, there wasn't any technology to implement it. It really didn't start showing up until the mid 70s. The technology caught up with the hardware technology caught up with this theory of fast Fourier transform. And so it took that, and one of the companies that was one of the first to introduce something that could deal with fast Fourier transform was this guy right here, Redicon Bucket Brigade charged coupled devices. And I had a couple of these that I played with. You could build a spectrum analyzer with that using FFT, using this Redicon Bucket Brigade. And several manufacturers did introduce them, but it was great for spectrum analysis. It was a good application for it, but it took a while. But 1984. E-Systems, which is now Raytheon, part of Raytheon, my former employer, they came up with a term called software radio. And this is kind of that origin of software defined radio, but they came up with a thing called software radio. It was a digital baseband receiver, and it combined things like interference cancellation and the demodulation of a modulated signal, all done digitally in software. And so that's kind of the first time that that shows up in the public domain or out in the, I'll say, the open world. There was plenty of stuff going on in the secret. I won't call it the black. Well, I could call it the black world. You know, of developing stuff for the Defense Department and what have you that were doing things at software radio. But this was the first time that it actually showed up where people heard the term. But it wasn't until 1991 that we heard the term software-defined radio, and this came out in an IEEE Telesystems conference in 1992. It was published by this guy, Mottola, the software radio, and he coined that phrase, software-defined radio. Well, what makes software-defined radio work? Well, it's Fourier. You know, this. I'm sorry, I'm distracted by chat. I'm taking a look at chat because this goes back to Nyquist sampling theory and all that. That all makes that all these things all tie together. But Fourier, if you're familiar with Fourier, the Fourier series is an interesting mathematical tool that allows you to define a periodic, important point, periodic signal can be represented by adding and subtracting harmonically related sine waves. Well, that's all fine and dandy, but what radio signal is periodic? It's aperiodic. It's, you know, human speech. So Fourier series isn't going to do us much good there, but there's a process called Fourier analysis where we can dissect that signal, and it is extremely intensive calculation, and it's tedious, and it's not the thing you want to do. It doesn't lend itself easily to non-periodic signals, speech. Okay. What does, on the other hand, is something called a Fourier transform. And the Fourier transform actually shows the relationship between the time and frequency domains, which is what we're interested in when we want to demodulate a non-periodic signal. We want to look at it in the time and frequency domain. So again, the Fourier transform, they can be sampled, Nyquist sampling theory, and transformed using a discrete Fourier transform, but still takes a lot of horsepower to do that and not very practical. But now we can throw in a fast digital signal processor, those DSP chips, and what do we get? We get the fast Fourier transform. So now we can use FFT. It's a form of the discrete Fourier transform. It's a family of algorithms that belong to the discrete Fourier transform. We use that as the basis of virtually all we do with SDRs. That's really where we go. And of course, we use this for all kinds of stuff. Spectrum analyzers use FFT. I mentioned the SDRs, all of our SDRs, the Flex, and all these use FFT. It's a real common algorithm to be used in digital signal processing. So I'm going to throw up some alphabet soup. I'm not going to go through all this stuff. I'm just going to flash this stuff up there. A lot of terms that come out of SDR, and some of them you're probably familiar with: FDMA, TDMA, time division multiple access. Some of the interesting ones: QAM, quadrature amplitude modulation, QPSK, PSK, phase shift keying. We know that one. But all these things all evolve out of or evolve into SDR. So anyway, we won't go through all that stuff. But in amateur radio, I think the first time this really showed up was Gerald Youngblood. You may recognize that name also. I certainly do. Published articles in QEX in 2002 and 2003, a series of articles on SDR, and introduced something called the SDR 1000 and introduced flex radio systems. So Gerald Youngblood was the guy behind all of that. So that was probably the first SDR to show up in the amateur radio, was that SDR 1000. You could purchase the pieces of that through Tapper. So that was an interesting way to do it. It was sold as a kit through Tapper. You'd buy the modules and put the thing together. I never built one of them. I wish I had now. Would have been interesting to experiment with. But the question arises, and a lot of people ask this question, just what is an SDR? What is a software-defined radio? Well, let's talk a little bit about that. We're going to explain this a little bit because a lot of this, I think, remains mystery to many, many people. I think I can clarify a little bit of it. I won't go into some super detail of it, but I will give you enough of a taste of it that you understand what's going on. Okay. So typically an SDR consists of multiple stages. You start out with an RF stage. This is your basic SDR. RF stage followed by what's called a quadrature mixer, or the IQ mixer, if you've heard that term before, IQ mixer, an A to D analog to digital converter. Okay, you've got to have an analog to digital converter. You do some digital signal processing. There's your FFT stuff and all that. You put that out to a digital to analog converter, right? A D to A converter on the output, and you amplify it and deliver it to the user. So that's all the stuff that gets used here. And I liken this to, I mentioned this earlier, and it sounds a lot like Weaver. When you start comparing these things, it's a lot like Weaver modulation. The idea of using a quadrature mixer, an IQ mixer. It's an interesting thing. So let's talk about that IQ mixer. You hear this term all the time. What is an IQ mixer? It's a quadrature mixer. It is really the heart of the basic SDR. A quadrature mixer produces two signals that are 90 degrees out of phase with each other. So you take your initial signal and you shift it 90 degrees, you get two signals that are out of phase now. So the I in IQ is the in phase signal, and the Q signal is the quadrature signal, or the 90-degree phase shifted signal. Now, Flex calls it something different. In their radio, they call it a QSD, a quadrature sampling detector, but it's basically the same thing. And a common term you'll run across is that it's a TALO mixer, the TALO mixer. That's this IQ mixer. So what is the IQ bias? Well, I'm going to give you an example, and we're going to demodulate an AM signal in an SDR. We're just going to go through the simple process. It's really simple. I take my in-phase signal, and what does an in-phase AM signal look like? That's what an in-phase AM signal looks like right there, right? It's a modulated carrier, right? Now, if I shift that carrier 90 degrees, my Q signal, I get this. Now, if you note, at any given sample, I sample the two signals at the same time here. When I sample the in-phase component, I get this magnitude, and this is a magnitude. Keep that in mind. And when I sample this guy at the same time, I've got a magnitude of 0, but this is my peak magnitude, right? And each of these samples has a corresponding sample in the in-phase and the quadrature component. Now, if I take the difference between those two signals, the in-phase and the quadrature, what do I get? I subtract Q from I get a sine wave. I just recovered the audio from an AM modulated signal using an IQ mixer. And it's as simple as that. That's how it works. That's about as basic as I can get. I've looked and looked for a really good explanation that hopefully everybody can understand. I think this is one that everybody here can understand that. And of course, for those that really understand it, this is like, yeah, go away. Right. But I think it's a good way to describe it. And it shows AM is, of course, real simple. We could have a lot more complex system here. And instead of this I minus Q, which demodulates AM, I can have some other complex algorithm there to figure out what's going on in my modulation scheme. So that's the key to it. So there you go. SDR, simple. Well, in 2000, I think Flex, I'm watching the time. I'm running a little over here. I've only got a few more slides to go here. We'll go through them. I think for 2000, this was really what really showed up as a kind of a state-of-the-art receiver transceiver using front-end filters, that quadrature sampling detector, high performance A to D, and that's the key to it, is a high performance A to D um, converter. Lots of bits, lots of dynamic range. That's important, and it offloaded a lot of the work to the PC. And that's where all your filtering and demodulation took place, was on the PC. Well, PC really isn't a DSP. It's using the PC, but it was kind of a neat system. In fact, I've got two of them here, and I loved that radio. The 5000 was wonderful. It was an incredible receiver transmitter, but it did have its issues. But you guys are all familiar with this. This is the quick and dirty SDR, and these have been around for quite a while, at least 10, 15 years now, using an RTL USB dongle, which of course was developed for over-the-air television in Great Britain. But we can basically repurpose that SDR dongle to be a receiver. And it's based on this RTL 2832, which is basically an SDR chip. And it uses this Elonix 4000 tuner. And these things were really cheap. You could pick one up for less than $10 on eBay and add some free software to it. And what do you get? You get a receiver that tunes from 60 megahertz to 1700 megahertz. Pretty cool. And yeah, I'm sure many of you guys played with these things. I've got them, tons of them around here, all kinds of different stuff. FunCube was developed. FunCube was kind of similar to that. I think it used that same RTL 2832, but it was developed as an inexpensive receiver for CubeSats back in the day. So that was kind of a neat application. Again, decent performance at a low cost. So you tune 150 kilohertz to 240 megahertz and 420 megahertz to 1.9 gigahertz for that satellite that he developed it for. So these are all great tools. These things are great tools for learning about how to use it, how to play with SDR and how they work and all of that. So here's the RTL dongle. There's the guts of an RTL dongle. And the SDR Sharp is one of many SDR software packages. There's lots and lots of them. Okay, we're getting there. We're almost there. This really is what I consider defining moment 15, was the direct sampling software defined radio. This is a game changer. And I think the first commercial product that used direct sampling in the public domain that we could get to as mortal humans was this guy, this Micro Telecom Perseus receiver. These things are incredible. It was not cheap. That was a $1,600 box back in the day. But this thing tunes DC to 40 megahertz, and it can do that in one chunk. What you see there is one sweep of basically showing you the entire spectrum from DC to 40 megahertz. Now, that's not a very practical application of it, but it has a very wide dynamic range, and very few spurious emissions. There are very few spurs on it. I still use it. It's a great little radio. I love this thing, and it uses a PC. But they were not cheap, and I think it still kind of holds its own today after so many years. That came out, well, late, no, let's see, when did that come out? Probably around 2010 or so, 2009, maybe, somewhere back then. It's over 15 years ago they've been around. But that was the first one to use this direct sampling idea. And this made really a game changer. But along comes Flex Radio with this guy, and I say they upped the game. This is their 6000 series. And of course, I've got one of those sitting behind me here on the rack, 6700. It's a direct sampling receiver. The performance on this thing is staggering. It's network connected. The bulk of the work is done in the radio. In other words, it doesn't offload stuff out to the computer. It's Ethernet connected, and the computer what's running on the computer is basically just the GUI. It's how you manage this radio, the Smart SDR software. And then they introduced this one, which is kind of, if you're into receivers, the 6700R is a receive only model. It's a direct sampling receiver, but the performance of these receivers is pretty staggering. It's 245 megasamples per second. That's for both all of the 6000 series, 245 megasamples per second. It'll tune 30 kilohertz to 77 megahertz directly, and it'll tune 135 to 165 megahertz. So you directly tune, receive 2 meters. Okay, so that was kind of a neat little radio, and they were still, I think, they still hold their own. Still hold their own today. There's a lot of other options out there we'll talk about. I'll throw a few of those up here. Some of you guys may have some of these guys. I think some of the options that come out today are things from Apache Labs, the Non 8000. That's their top of the line. Of course, Elecraft, Elecraft K4. What a great radio! Really great piece of equipment. ICOM has the 7610, but I like the 7300. It's a low price, great price point, and I think there's probably more of those things have sold than probably most any other radio. I would wager to say that more than half of you guys here on this tonight have 7300s, maybe even more than one of them. That's a nice little radio. And of course, the 9700 is the VHF, UHF version. Yaesu recently introduced that FTDX 101, another direct sampling SDR. Nice piece of gear, very expensive. ELAD this is basically a module that they produce that's an SDR. You'd have to wrap a bunch of other stuff around it, like software. But something that's kind of fun, if you've never run across this Great Scott Gadgets, Hack RF1. This is a learning tool, and this allows you to, using a graphical user interface, be able to develop modulation schemes for SDR. So this is a transceiver. It's a transmitter and receiver. It's very wide range. They're not cheap, but they're not terribly expensive. It's a hobbyist thing. I mean, it's a great hobbyist thing, and they're kind of fun to play with. I've got one here myself that I've played with quite a bit. It's a pretty neat little unit. Another one like that you may have heard of is this Red Pataya SDR Lab 12216. I guess it's a basic module. You're going to have to wrap some other stuff around it to be able to use it. And of course, the other guy, another entry in there is the Xiegu G90, another SDR. Okay, I've got it. I said I wasn't going to really bash anything, but there is a radio that I have to bash. I have to, because it cost us dearly. If you've ever heard of JTRS, Jitters, as its nickname, as it's unkindly spoken of, JTRS, Joint Tactical Radio System. This was the DoD's Swiss Army knife radio. Now, the reason I'm going to bash this radio is because working for Raytheon, working for Hughes Aircraft Company, then Raytheon, we had a product called EPLARS, and EPLARS was the key. It was we called it the battlefield internet. It was a digital IP communicating radio that ran on UHF, that used spread spectrum, frequency hopping, encrypted system. It was an incredible system, and it was the backbone of the military or the Army for decades. It was introduced in the late 80s, and it's been around. And this was supposed to replace that, but it was supposed to be a do-all for everybody. So it was actually based on some early DARPA work called Speakeasy back in 1991, is that what JTRS is based on. It was to replace all, and I mean all, tactical radios. And there's lots of tactical radios. They use all kinds of different schemes, all kinds of different radios, multiple form factors using different waveforms. Now, there's a term that I'm introducing. If you've never heard that term before, waveform is another way for basically a modulation scheme. Just a fancy name for it. Digital modulation method. The Flex supports different waveforms, but EPLARS was a waveform. The one that I worked on with JTRS was called Soldier Radio Waveform, SRW. There were lots and lots of them. Anyway, there's so many of them. JTRS was required to support all of those. It was required to switch between waveforms on the fly. In other words, I'm talking to this guy on this radio, and then I'm going to talk to this guy over here instantly on a different radio using a different waveform. Oh, and guess what? It's encrypted, so it's using a different encryption scheme. So I've got to switch keys and switch encryptors and all on the fly. Crazy. Needless to say, it sank. And I think we got to be thankful for that. This program spent billions of dollars and was billions of dollars overrun and years behind schedule. That radio, which was the one I showed a picture of at the first slide back there, that's the GMR, the ground mobile radio, weighed 400 pounds. It took 20 minutes to boot up. Yeah, gross waste of taxpayer money. Dennis's opinion, okay. I'm one of those taxpayers, even though I worked on, I didn't work on JTRS. Well, I worked on Soldier Radio waveform, SRW. We built a radio that used SRW. So that was kind of cool. But this whole program, well, 2012 gone. And I love this. Our assessment is that it is unlikely that products resulting from the JTRS GMR development program will affordably meet service requirements and may not meet some requirements at all. Therefore, termination is necessary. So that came from the Undersecretary of Defense in October of 2011. By 2012, program's done. So probably a good thing. Anyway, but in terms of technology, where do we go from here? What's going to happen next? There you go. Oh, I love it. Who made the comment there? You got to pick the right prime. Yeah, they did not. No question. John, N6VEG. Yeah. Yeah, I have to believe that would have been a better choice. But if you think about it, this is Dennis's opinion. You know, Hughes Aircraft, we developed EPLARs. We had the knowledge and the technical knowledge and the skill. We bid on it, didn't get it. We probably should have been the prime on JTRS. It probably would have worked had we gotten that, but who knows? Oh well. Anyway, where do we go from here? Let's talk about that. Hello, where are you? Come on. There it is. Okay, I was wondering where that disappeared to. Direct sampling. Okay, so direct sampling, this is the trend we're seeing today, direct sampling receivers. Improvements in performance. We're going to need higher and higher performance A to D converters. That's a key thing. Getting higher performance, meaning higher sample rates, wider bit width, so more dynamic range. This is key. And of course, getting those performance issues up means more bucks. So they are going to be expensive, but the higher sampling rates, I mentioned more bits, greater dynamic range, portability. That's another key. But just think about the ability to capture the entire VLF, HF, VHF, and UHF spectrum, capture and record it, and then play it back later. Tune, control it remotely, like over the internet. You know, how cool would that be? We get everything everywhere all at once. Oh, wait a minute. Wasn't that a movie? Yeah, I think it was. Anyway, I'm going to close with this. Could this be your next receiver? This is the PerVisus Cyan. And this is one heck of a radio. Covers DC to 18 gigahertz. Yikes. It can run up to 16 chains combined of receive and or transmit. 16 chains. 1 gigahertz bandwidth per chain, and that's upgradable to 3 gigahertz bandwidth. It's based on an Intel Stratix 10 FPGA system on a chip. Now that chip right there, this thing is staggering. This is capable of doing single precision digital signal processing up to 10 teraflops per second. Let that sink in. That is ghastly. Wow. You know, 245 megasamples per second here, and these guys are talking about, you know, incredible speeds. Well, let's talk about cost. What do they say if you have to ask? Any idea what this thing goes for? Entry level, $100,800. Entry level. The fully configured model is $280,350. I don't think I'm going to be running out and buying a couple of these for my station, but you know, it's nice to dream. But who would be using these? You know, I would expect that things like FCC, you know, doing spectrum monitoring, this would be exactly what they would use, is one of these things, or 2 or 3 or 4 of them. Yeah, government surplus, right on. Yeah, we know they'll show up someday, but that still won't be affordable by humans. They're one of those things that's affordable by governments, unfortunately. But anyway, that's it. I'm going to leave you with that. I think that's a pretty spectacular piece of hardware right there, and I'd love to play with one someday. Maybe I'll have to find out. Anyway, there you go. All done.
Okay.
Oh, and only 20 minutes. So yikes. Ah.
I'm mentally prepared for this. Okay. I got my stuff up here. Anybody got any questions? Raise your hand. You've been keeping up with chat there, putting Barry out of business.
Everything's up to date in chat.
Yeah.
Let's see, third order dynamic range and narrow spaced advantage, disadvantage between superhet versus direct sampling SDR. Oh yeah. Hmm. Yeah, that we could probably do a whole presentation on that. Um, I would suggest, rather than listening to me try and describe that, go to I can't even think of it. Who does the receiver evaluations? Sherwood Engineering. Yeah, if you look at Sherwood Engineering, and he's got on his website, it's SHERWENG. Sure. Oh, yeah, I think that's right. Is it WENG? I don't. Sherwood Engineering. He has a whole section on his website devoted to describing things like exactly what you're asking right there. And he does a really great job, much better than I could ever describe. And of course, he ranks the receivers, and it's a pretty interesting table. And it's been interesting to watch that. I don't know if he's got old copies of it. It's been interesting to watch that over the years because I've been following that for quite a while. And it's interesting to see how things move around as different manufacturers bring out new things, and something that's 20 years old may be up in the third place on the list, which is kind of amazing. But that's a great question. Um, let's see what else we got. Painful to use the GMR. Yeah, I would certainly agree with that. Gene used to work for Uncle Ray, huh? Ah, Arlington? Oh, yeah, okay. Gonkulators, yeah. Okay. All right, I think that's it. No questions? No hands up? Well, gosh,
I think you did a pretty good job.
wow.
Either that or you put everybody to sleep, but I think it's a good job.
Yeah, hopefully I didn't put everybody to sleep. Oh, our
Yeah,
rodent
very
Schwartz.
certainly.
Yeah, EB500. I've got a couple of rodent Schwartz receivers here, but they're VHF, UHF receivers. But I'm working on getting an HF one, which is kind of cool.
Candace did put my cat to sleep.
Well, he was been asleep. Yeah, that's one of two rodent Schwartz receivers that I have over there on the table behind me. The other one's that covers like I can't remember, was it 50 to 1,000 megs, and the other one I've got covers like 20 to 2,000 megs. They're basically EMC receivers, is what they are, electromagnetic. Uh, what do you call it? Compliance EMC when you're doing testing compliance for interference and things like that in a radio. That's basically what those were used for. But they are high performance receivers. Whew. But yeah, RNS EB500. Yeah. Yeah, Roden Schwartz makes some pretty spectacular stuff.
Okay.
There you go, Sherwang.com. Thank you, Dan.
Oh, you're welcome.
Yeah, that's no the other Dan.
I know.
Our other Dan, my
My,
boss.
my pleasure to be of service.
Thank you, sir. My boss. And yeah, that is a great, that link right there will take you to probably one of the most useful informations you'll ever find if you're in the market for a new radio and you want to see what's out there and what the performance is like. Sherwood does a great job. And I'm really sad that he's done away with, he had some products that he marketed years ago for Drake and others, and the Drake mods for the R4C receiver were that just turned into just a monster receiver with the mods that he made to it. So anyway.
Yeah. Okay.
Well, great presentation. Very interesting history.
Thank you, Barry. I appreciate that. Oh, Yeah, it's a you understand why I broke it into two. It probably should be broken into three sections.
Well, I think last time we had a lot more Q&A going on
Yeah.
here.
Yeah. Well, I don't know. You know, my heart is in that last, my heart is really in the last one. I really, really love the early days of radio and the technology as it was developed and following that stuff is just really amazing to me. Um, you know, it's hard today to think about coming up with something new in technology. Yeah.
You want to see an interesting presentation on YouTube? Search for the transistor. It was done by AT&T Labs, and it
Oh
goes
yeah,
into
yeah.
all of the politics and all of the heartbreak and everything that went into developing the transistor. And one day, all of a sudden, it was Eureka, we've got it.
Yep.
No, you couldn't have it. We've done all this work for so long. We got to do it for a lot longer. No. Come over and take a look. Wow, what an amazing thing. And then they immediately called a press conference and they introduced it to the world, and the world hasn't been the same since.
You're right. It hasn't. It changed us forever. And it was an amazing development. And what it's evolved into today is just incredible. You know, I before pointed that, you know, point out things like cell phones, desktop computers. I mean, where would we be? You know, we think the country.
Transistors on a chip. It just boggles my mind.
Yeah, definitely, most definitely. Oh, I was thinking, who was it that IBM was that said, well, at most, I think the country's going to need maybe 3 or 4 of these computers.
Well,
Oh well,
RPA 6 transistor AM receiver.
yeah,
That was a big thing.
uh-huh.
okay, folks, we're running into lots of overtime here.
Yeah, we are.
Are there any questions? Anybody got their hands up? Anything else in chat?
Hands up.